So is this our third lecture on gas power cycles? We've basically introduced internal combustion engines. We spent a whole lecture, if not more, on Otto cycle, and today we're going to talk about the diesel cycle and then press forward. In review, the Otto cycle, so everything over here is review, and this is the new diesel cycle. So we can think about 4 states where the piston starts at bottom dead center, goes to top dead center. That's one stroke between state 1 and state 2. During that process, from 1 to 2, you have adiabatic compression. And then from 2 to 3, you have constant volume heat addition. Then from 3 to 4, you have adiabatic expansion. All of these are internally reversible. So if you have adiabatic plus reversible, that means isentropic. So S equal to a constant. And then from 4 to 1, you have that constant volume cooling. That makes up the Otto cycle. The diesel is very, very similar. So what we have is we have states 1, 2, 3, 4, back to 1 to make a cycle. From 1 to 2, adiabatic compression. Is there any difference? It's the same. But what we're going to find is the compression ratio, R, for a diesel will be a lot higher, double, 18, 20, something like that. Let's just throw out a number and say it's around 20 for the compression ratio. Where over here for the Otto, for gasoline, it's more like 10 or a little less than 10. Okay, what was exactly the definition of the compression ratio? Is it the specific volume at state 1 divided by the specific volume at the end of the process, state 2? Yeah, that's right. Okay, then the process 2 to 3. Instead of being constant volume, it's constant pressure heat addition. So now you're adding heat, and as you're adding heat, its temperature wants to go up and will go up. The pressure wants to go up, but you're going to let it expand such that it has a constant pressure. So notice that the location of the piston has changed. There's been some expansion. Now what happens in the actual diesel cycle is you don't have a spark plug, you have a fuel injector. And in that fuel injector you spray in the fuel after the piston or near when the piston gets the top dead center. So in our analysis, it gets the top dead center, you start spraying in the fuel, it starts to expand, you're burning, you're combusting, hence it's constant pressure heat addition. All right, so here we're going to have a new parameter, RC. All right, this is very confusing. R for a ratio, just like R, the compression ratio, it's going to be a ratio of the volume when you stop the fuel or stop the constant pressure heat addition divided by the volume that you started. That's called the cut-off ratio. Cut-off ratio. Why do they call it the cut-off ratio? It's when the pressure is no longer constant as you are expanding. So it's like the fuel has been cut off. All right. Now this is very, very confusing because what was the name of this other R right here? Compression ratio. C for compression. So C for cutoff. So you just have to know that, okay, I wish they would have maybe put a different symbol. Maybe they should have put RCOMP and then RCUT, something like that, but they don't like long subscripts. So you just have to know R without a subscript is the compression ratio. R with the subscript C is the cutoff ratio in this textbook. All right. Now, from 3 to 4, you have continued expansion, and it's now back to adiabatic expansion. It's back to being adiabatic and reversible, hence S is equal to a constant. But S is not a constant from 2 to 3, is it? Entropy is not constant from 2 to 3 because you're adding heat. As you add heat, you're bringing in entropy into the system. All right, so it expands from 3 to 4, and then 4 to 1 is the same as the Otto. you have basically constant volume heat rejection. Do you see that? All right. So maybe I can do this. Could you sketch a pressure volume diagram for the Otto? Does it look like this, 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 1 to 2 to 3 to 4? What does the pressure volume diagram look like for the diesel? I'll pause, walk around. Okay. But anyway, a lot of you had it. It's not the very hard question, is it? You start maybe with the same volume at bottom dead center. The only difference you could do here is maybe let it get a little closer to the y-axis because it is going to be a higher compression ratio. Then it's going to be higher pressure, but then you're going to have constant pressure heat addition, and then you're going to expand, and you've got to stop to have constant volume heat rejection. So state 1, state 2, state 3, state 4. If you can get the diagrams and then get the TS diagram as well, it'll really help you as we go and solve these problems. Let's continue on. So we just sketched that PV diagram. And again, it's pretty crude, 1, 2, 3, 4. And then a TS, isentropic. Then we have constant pressure heat addition. It's a isentropic expansion from 3 to 4. And then we have constant volume heat rejection, 1 to 2 to 3 to 4. All right, so the big difference again, constant pressure heat addition. If we take a look at the first law for the process 1 to 2, is anything really different? No, it's the same. So it's adiabatic, so Q1 to 2 is 0. How about the first law for the process 2 to 3? Before, for the Otto, this was 0. Is it equal to 0 for the diesel? It's not 0. It's not equal to 0 because it's expansion, boundary work. All right. So how do we calculate that boundary work, work 2 to 3? Integral PdV, and we like that. So the work 2 to 3 is the integral PdV from 2 to 3, and so this pressure is a constant, makes it a very easy integral, and so we're left with the pressure times V3 minus V2, or you could put, it's the same pressure, 2 is equal to 3, so when I multiply by V3, I put P3, and when I multiply by V2, I put P2. You can calculate that work just by knowing that pressure and the change in volume. For the cutoff ratio, R sub C, that was V3 divided by V2, true? So you can manipulate this a little more, but I think the algebra, it gets the point. You can substitute for V2, or V3 is R sub C V2. All right, that's the work 2 to 3. So now what you can also do is go back to this equation, first law, and you can throw this work 2 to 3 to the other side. So we'll have U3 minus U2 plus work 2 to 3 equal to Q 2 to 3. Replace that work 2 to 3 by this PV terms, and you'll get U3 plus P3 V3 minus U2 plus P2 V2 equal to Q 2 to 3. Do you see the algebra? And then we make the observation. What do we observe? That's a definition of enthalpy. So this is H3 minus H2 is equal to Q 2 to 3. Let me encourage you to make some notes on that. Let me encourage you to think about it. Because every semester that I've ever taught Thermo 1 or Thermo 2, where I cover the diesel cycle, I get questions. And usually they're scattered all over, maybe right before the final exam, something. They say, how come for the diesel cycle the heat in is a delta H? Q in, isn't this Q in? It's equal to a change in enthalpy. And then for the Otto cycle, it's a change in internal energy. I don't understand. Well, this is the best explanation I can give, right? So we have a constant pressure heat addition while you're adding heat, it's expanding. You have to add actually more heat for the same temperature change because it's doing work, it's boundary work as it's expanding. All right. The only other thing is for process 3 to 4, it's still adiabatic, but to calculate this work 3 to 4 is equal to the negative of U4 minus U3. And think about specific heats minus C sub V T4 minus T3. Okay. How do I calculate that T4? How do I calculate that T4? We had S equal to constant, but it's expanding only from V3 out to V4. What was our equation in order, given T3, how do I calculate T4? So what would it look like? I should have scooted over because I'm not going to have room for the exponent. I pause, walk around. All right, so let's go ahead and pick it up here. So what we're going to do is we're going to have a ratio of volumes to the K minus 1 power. I'm using the equations for constant specific heat. And in this case, what would be that relation? Would it be V4 divided by V3 or V3 divided by V4? Which one would it be? 3 over 4, right? All right. I still didn't leave enough room for this. Well, I'll do it right down here. Take a look at this. I want to get the V3 and I want to divide it by V4, right? If I put a V2 here multiplied by a V2, is that the same thing? So what we can do is we can replace that V3 over V4 by V3 divided by V2, R sub C. What is V2 divided by V4? V4 is the same as V1. That's right. So this will be T3 to the cutoff ratio divided by the compression ratio to the K minus 1 power. So this gives us the temperature of 4. Just a little more work than the Otto cycle, but it's the same equations. All right. So the strategy when you solve a diesel, know what state 1, 2, 3, 4 are, know all your 4 processes, be able to put on a diagram, PVTS, be able to apply the first law, walk around and build a table for each of the states and a table for all of the transfers for each of the processes. You can also work out an analytic expression for the thermal efficiency of the diesel cycle. It's in the textbook. It's also an equation sheet. Here's the equation. The thermal efficiency, it looks a lot like the thermal efficiency for the Otto. 1 minus 1 over R to the K minus 1. That's the thermal efficiency of the Otto cycle. But what we have for the diesel is you have the same 1 minus 1 over R to the K minus 1 times what's in this square brackets right here, which is R sub C. I forgot. What is RC, the name of it? Cutoff ratio raised to the K power minus 1 divided by K. I forgot. What is the name of that lowercase k? What is K? Ratio of specific heats. We're just working with air. At low temperature, room temperature, it's 1.4. As it elevates at temperature, higher temperatures, it'll nudge down from 1.4, 1.35, 1 point something. All right. So we have K times R sub C minus 1. All right. So if you would like to see the whole derivation, in the interest of time, I don't repeat it this semester. Okay. Ready to solve a problem? Just like the Otto, it's a long problem, but let's jump into it. You have air. This is the typical working fluid in a diesel cycle. They give you the pressure and the temperature at the start of the compression stroke. That's state 1 in our nomenclature. And it's an air standard diesel cycle. All right. Compression ratio is 20, and the cutoff ratio is 2.2. use constant specific heats where this value is CV and that value is CP. If you do the ratio, you'll get K is about 1.40. All right. And then you have a bunch of questions. Temperature at the end of the compression stroke, there's the answer. So what I would do again is I'd plot, get your PV diagram and your TS diagram. And let's make a little table for all of the properties. And the pressure in kilopascal and the temperature in Kelvin are the critical ones, state 1, 2, 3, 4. So for the pressure, we're given that it's 98 and the temperature 310. So how do I calculate T2? It's just like what we did for the Otto cycle. It's T1 raised to the compression ratio, or times the compression ratio raised to the K minus 1 power. How do I get P2? There's two ways at least to get P2. How would you get P2? Yeah, if you have T2, you can always use the ideal gas law. So the ideal gas law would give us that it's R T2 divided by V2. And what is V2? Is it V1 divided by the compression ratio? And you get V1 by RT1 divided by P1. I mean, there's a number of ways to get it, so you could substitute there. You would get that the RT1 divided by the little lowercase r P1. And then you could substitute in here. You have RT2 divided by RT1 RP1. All right, you can see some cancellation. You could do that. There's another way. Yeah, so we remember that we have P2 divided by P1 is equal to V1 over V2 to the K. I encourage you to do it both ways, multiple ways, and then you'll find, build confidence in how you solve a problem. But this will work. You could get P2 is equal to P1 times the compression ratio raised to the K power. All right. Maybe there's another way. I just would need to think about it again. But you would get these pressures and temperatures. All right. Which one of these, how about P3? How do I get P3? It's equal to P2. It's the same. So P3 is equal to P2. It's constant pressure. How about T3? Would I use an equation like this or like this to get T3? Is the process from 2 to 3, is that isentropic? S constant from 2 to 3? It's heating. It's being heated at constant pressure. It's definitely not isentropic. Don't ever use one of those isentropic relationships for a non-isentropic process. So how do I get T3? How can I find T3? It always behaves as an ideal gas, and I'll write the equation at state 2. I'll write the ideal gas equation at state 3. And so what you do is you say this is, let me just write it out, P2 V2 is equal to RT2, true? So if I just divide by T2, then what I get is I get that P2 V2 divided by T2 is cap R. Is that also equal to P3 V3 divided by T3? And here you can say, okay, the pressures are the same. And so T3 is T2 times V3 divided by V2. And what is that ratio? Cutoff ratio, yeah. And so you just work through the system like that. And we already talked about how to get the temperature at 4 from 3. That was the last slide or slide before. Likewise, the pressure, the same thing. Isentropic expansion from 3 to 4, but watch out, it's not 1 over R, it's R sub C over R. Okay, so once I get those pressures and temperatures, the critical data is the temperature column, then we can get a table of transfers. Then we just work through the problem solving for peak pressures, peak temperatures, heat additions, etc. Let me show you the solution to this problem. There it is. So it's set up and solved in Excel. Just the basic data. This is the state. Notice I added a column of V's. It's nice. But it's not essential. You could do it all just P's and T's. The table of the transfers, and then calculate the thermal efficiency. This thermal efficiency, how do I calculate it from the data above? The cycle thermal efficiency for the diesel cycle. How do I calculate it? That's right. The net work divided by the Q2 to 3N. That's the only QN. And that'll come up with the 63.8%. Then you go back to that cold air equation for the thermal efficiency of the diesel cycle, one that I showed, didn't derive it, and boom, you get the same value. Then the mean effective pressure. What does the cycle look like, this cycle, with the 20 compression ratio, 2.2 cutoff ratio? What's it look like on a real PV diagram? There it is. It's a lot different than our little cartoon PV diagrams, but there it is, okay? So the pressure goes way up as you get close to top dead center. And then you have constant pressure, heat addition, and then it drops dramatically as you isentropic expansion. Any comments on that? Look good? Well, what did we do once we did it for constant specific heats with the Otto cycle? Redo with variable specific heats. So let me just show you, it's the same type of strategy. You're using the table A22 and you're using the V sub R's when you have isentropic processes. And so we have 2 of those processes that are isentropic. From 1 to 2, S is equal to a constant. From 3 to 4, S is equal to a constant. Does it change our numbers? Absolutely. And does it change the thermal efficiency of the cycle? Yes. So this is the new thermal efficiency accounting for variable specific heats. There's a little thing that what happens is if you completely use table A22 for the internal energy and enthalpy values, the enthalpy values when you interpolate in the table can be slightly different than if you just use the equation H is equal to U plus PV for an ideal gas. PV is equal to RT, so U plus RT. All right. So I did a little comparison out at 2,000, 2,100, 500, 2,200. I look at the U value, I look at the H value out of the table, and I look at H calculated by U plus RT. What is R again? It's just R bar divided by the molar mass of air. And it doesn't seem like a big difference between these 2 values, does it? 0.025%? You know, 0.021%. Just think of it. You're a parent, you charge your child with a $20 bill to go buy something at the store. They come back and you're going to holler at them if the change is off by 0.02%. That's like a penny or something. No, you're not. It's not a big deal. But this little bit of error, if you put the delta H with the linear interpolation into this for the Q2 to 3, when you do the sum, you will not get Q net equal to work net to 4 or more significant digits. So I just point that out. So if you're checking me and you say, hey, I got it to 3 significant digits, but not 4 or 5 significant digits, it could be because it's linear interpolation in a table that actually has data. That's why they put a table. It's not all straight data. It's approximation. when you linearly interpolate. All right, but I used this for the H. I used this value for H3 instead of that value for H3, and it's good to it. I actually checked it like 6 digits. It's good to 6 digits. All right, that's a little aside. You probably could have gotten through this whole class without that knowledge, right? So let's press forward. What metric do we grade gasoline by? When you go up to a pump, you want to buy gasoline, you typically have 3 selections. And what other, I mean, you're going to pay more for, but what are you paying more for? Higher octane number. And octane is resistance to self-ignition. And if you have a high compression engine, it will have a tendency when it gets near top dead center to fire or start to explosion even before the spark sends it. Or if the spark sends it, it'll start in other places at the same time, and then you'll have this knock issue. All right, so if you might have to pay for higher octane, pay more money for a gallon of gas. What about diesel? Anybody bought diesel? You go up to the pump, how many options do you have? 3? 1 option, don't you? That's it? Why do we? Well, anyway, they do have a cetane number for the diesel, but it's pretty generic. It's just 1 option. Number 2 diesel is as typical at pumps around. Every now and then you'll see the number reported, but most of the time it's not even reported. It's basically low sulfur diesel. That's it. Number 2, low sulfur diesel. But if you want, you can look about how they characterize the quality of the fuel. The cetane number, the higher the cetane number, have a shorter ignition delay period than the lower cetane numbers. Another great video, I'm not going to show them, but how they show a fuel injector, how they spray it in, and what's the effect of the cetane number on combustion. Just want to show you this. If you own, let's say, a Ford, here's out of the 2000, what is that, 16 diesel. So if you bought a brand new Ford and it had that engine in it, like a big pickup truck, you could read the owner's manual. I know engineers like to do that, right? We like to read our owner's manuals. And you'll find that you should use ultra low sulfur diesel, number 1 or number 2, with a maximum 15 ppm sulfur. Does anybody remember? Probably not. You're too young, right? When they switched to the low sulfur, diesel used to be significantly lower than gas per gallon. Then when they implemented that you couldn't sell anything but 15 ppm or lower diesel, the price went up because the refineries have to work harder to get the sulfur out. Anyway, now it's all just 15 ppm. Okay, you may operate your vehicle on diesel fuels containing up to 20% biodiesel, B20, but do not use home heating oil, agricultural fuel, raw fats and oils, waste cooking greases, biodiesel fuels with more than 20%. And do not add gasoline or gasohol or alcohol to your diesel fuel. This is an excellent video because what's new in internal combustion engines and automobiles? This video, put out by Bosch, so it's very commercial, talks about gasoline direct injection. Actually having a fuel injector in the combustion chamber and not a fuel injector in the intake manifold or throttle body or even what we used to have as carburetors. In this video they say by 2020, about half of the vehicles, new vehicles put out, will be gasoline direct injection. So a lot of things are still changing. They're getting rid of the cams. Somebody was telling me now you're going to have camless engines. The controllers on the valves are so good. So the world is completely being revamped in internal combustion engines, which is a good thing. This is a shot out of the equation sheet. Why do I show it? Because a lot of people will look at these two equations and they'll get them confused. Is there any words to describe this equation or that equation in your equation sheet? No. You kind of not have to know what they are, right? And this one is good for the what cycle? And this one's good for the diesel cycle. Perfect. Don't make that mistake. This is a little summary for internal combustion engines, kind of know how they work. Piston, crank, connecting rod, valves, intake, exhaust. Otto cycle is approximation for gasoline engines. Know how to solve problems, constant, variable, specific heats. Get the temperatures, get the pressures, get the Qs, get the Ws for the processes, get the thermal efficiency, get the... Did I say backwork ratio? What should I have said? I'm on autopilot right there. The mean effective pressure. Whoops. And then the same for the diesel cycle, MEP. Well, thank you very much for your attention. We'll see you next time.